Welcome to the Deep Dive. I'm Vivian Hong.
And I'm Dr. Sun Hom.
So if you've ever just stopped and, thought about the air around you, that huge blanket of nitrogen, about 78% of our atmosphere, you're breathing in what is basically one of the most stable things on the planet.
It's incredibly inert.
Right. But today, we're diving into this monumental quest in chemistry. How to take that super chill gas and, well, turn it into maybe the most powerful and cleanest explosive ever conceived.
It's a fascinating challenge of energy density. And our source material for this, we've got technical papers, some really high-level computational models, and a truly groundbreaking report from the journal Nature. It all shows that chemists are, well, they're finally getting there. They're creating what you could almost call a nitrogen bomb, hidden in plain sight.
So our mission today is to unpack the science behind these things called polynitrogen allotropes, or NA. We're going to look at why it's been so hard for decades to make them.
And we'll get into why the recent isolation of something called hexanitrogen N₆ is such a massive moment for the field.
And then we'll look at the theoretical side, what physics predicts for molecules like an N₆ cube, and how that could just completely revolutionize things like space travel and defense.
It really all starts with stability. I mean, if the periodic table had, like, an accountant, it would be N₆, the nitrogen molecule. It just sits there, calm, inert, and unbelievably stable.
And when you say stable, we're not just talking about something that's, a little hard to react with. This is a chemical fortress. So why? Why is that one molecule so stubborn?
It's all because of the unique bond holding the two nitrogen atoms together. It's a nitrogen triple bond, NU.
A triple bond, so 3 links between them.
Exactly. 3 pairs of electrons are shared, and that linkage is really, really short, about 110 picometers. And because it's so tight, it takes just a colossal amount of energy to break it.
Okay, how much energy are we talking about here? Give us some perspective.
The metric is dissociation energy, and for NUs, it's 945.41 kilojoules per mole.
Wow. And to put that into context for you, a typical carbon single bond, the backbone of almost all life, right?
Yeah.
There's only about 347 kilojoules per mole. So the N bond is nearly 3 times stronger.
It really is the gold standard of chemical stability, and that's why we use it for so many inert applications.
Right, like keeping food fresh in bags or purging fuel lines so they don't explode.
Exactly. And liquid nitrogen is a standard cryogen. It's everywhere, from our atmosphere to, believe it or not, the solid nitrogen glaciers on Pluto and Triton.
But the whole trick here, the goal, is that every time you manage to break that super strong triple bond and force the nitrogen atoms into a new, unstable shape like a chain or a cage, you've basically stored all that energy.
You've bottled it up.
Yeah. And the reaction we're interested in is when those unstable structures just snap back into that comfortable inert N₆ state, releasing all that stored energy in an instant.
A good analogy is a spring. Think of that N₆ triple bond as a completely relaxed, loose coil. The entire field of polynitrogen chemistry is about trying to compress that spring by forcing the nitrogen atoms into these new, strange structures like N₆, N, or N.
And trying to synthesize these has been a really long and difficult road, hasn't it? I mean, it's kind of like the search for carbon allotropes beyond diamond and graphite, which eventually led to fullerenes.
It has. The problem is always controlling that huge energy release. Any N₆ structure you manage to make is, by its very nature, unstable. It wants desperately to revert to N₆. Early attempts often just resulted in these fleeting molecules that disappeared or just violent, uncontrollable decomposition.
Before we get to the big molecular breakthrough, we should probably mention one way scientists did manage to do this years ago, right? The nitrogen diamond.
Ah, yes. That wasn't really a molecule, though. It was a polymer, a big network structure.
But it was a proof of concept.
It was, and it was a demonstration of the sheer force you need. To make this stuff, this single-bonded cubic structure, researchers put pure nitrogen gas under absolutely staggering conditions. We're talking 1.1 million atmospheres of pressure and heating it to 2,000 Kelvin.
A million atmospheres.
Yeah.
What is that? 15 million pounds per square inch. You basically need the pressure of the Earth's mantle to do it.
And that proved the potential energy was there, but it was nowhere near practical, which is why this recent breakthrough is such a paradigm shift. They synthesized a neutral molecule at far more accessible conditions.
Okay, so this brings us to the big one. The paper published in Nature in June of 2025.
This is the milestone.
Tell us about the team and what they made.
So the achievement is the successful preparation and isolation of hexanitrogen, N. The credit goes to Wei Yu Kennen, Artur Mardikov and Peter R. Schreiner from Justus Liebig University Gießen. And this thing they made, a linear N molecule, is the first neutral molecular nitrogen allotrope beyond N ever to be created and trapped.
Hexanitrogen. So 6 nitrogen atoms all forced into a single chain. How on earth did they do that without, crushing it with a planet's worth of pressure?
They used a much more, let's say, gentle approach. It was a gas phase reaction of chlorine or bromine with silver azide, and this was done at room temperature.
Okay, but if it's so unstable, how do they stop it from just vanishing?
That's where the real magic is. It's all about immediate stabilization. They had to instantly isolate it and freeze it. They trapped it in these argon matrices at a super frigid 10 Kelvin, or as a neat film at 77 Kelvin.
Which is the temperature of liquid nitrogen.
Right.
So you create the compressed spring, but you have to instantly flash freeze it to stop it from snapping back. Which brings up this kind of stability paradox. If it's so volatile, how can you even study it?
This is the beautiful dance between what we call thermodynamic potential, that's the massive stored energy, and kinetic stability. The kinetic stability is like an energy barrier, a force field holding the atoms in place.
Okay, break that down for us.
Think of N₆ as a giant boulder sitting in a little dip at the top of a huge hill. Thermodynamically, it really, really wants to roll down that hill and release all its potential energy.
But kinetically, that little dip it's sitting in, the barrier holds it in place, as long as you don't give it a push.
Precisely. And that dip is a dissociation barrier of about 14.8 kilocalories per mole. That barrier is strong enough that if you keep it really cold at 77 Kelvin, the calculations predict N₆ has a half-life of over 132 years.
132 years, so you can store it.
Under refrigeration, yes. At those low temperatures, the atoms just don't have enough thermal energy to jump over that kinetic barrier.
But if you warm it up,
Yeah.
You're giving that boulder a push with ambient heat.
You got it. At room temperature, about 298 Kelvin, that thermal energy easily overcomes the barrier. The half-life plummets to just 35.7 milliseconds.
Milliseconds, so it's gone in the blink of an eye.
Almost instantly. It just decomposes into 3 molecules of N₆. And that's why this was such a huge achievement, that they could synthesize and trap it at all. It was actually voted Molecule of the Year 2025 by chemical and engineering news readers.
Okay, let's get to the good stuff. Let's talk about power. That instant decomposition. What's the magnitude of that energy release? Put that into terms we can actually grasp.
When N₆ decomposes, the reaction is hugely exothermic. We're talking 185.2 kilocalories per mole. And when you translate that into performance as a high-energy material, the numbers are just phenomenal. Our sources calculate that N₆ can release 2.2 times the energy of TNT by weight.
2.2 times TNT. That's staggering. How does that compare to the current, state-of-the-art military explosives?
Yeah.
Like RDX or HMX.
It still outperforms them. It releases about 1.9 times the energy of those well-known HEDMs, but this is a game changer not just for the power, but for what it doesn't produce.
And that's the green advantage, right? The clean part. Why is that so important?
Well, think about traditional explosive or rocket fuels. They're all based on compounds with carbon, hydrogen, and oxygen. So when they combust, they produce pollutants, co-euro, carbon monoxide, water vapor. N₆ only contains nitrogen.
So the only thing that comes out is
Harmless, stable nitrogen gas, pure air.
So we're talking about this immense power, but with zero chemical pollution. I mean, you can imagine military uses where there's no residual toxicity or even bigger propellants for rockets, where the exhaust is literally just air.
The implications are transformative. But NU, as amazing as it is still really just a stepping stone. Chemists are always chasing the maximum possible stored energy, and that takes us into the theoretical realm.
Where the pressure comes not from diamond cells, but from supercomputers.
Exactly.
Okay, so this is where it gets really wild. We're shifting from what's been made to what computational chemists think is possible. We're looking at research here from Frontiers in Chemistry from 2022. The researchers are Qing Liang, C₂h-N₆, and a whole team from Nanjing University of Science and Technology.
And they were focused on the ultimate theoretical prize, a highly strained molecule called octazocubane, cube N4.
A cube of 8 nitrogen atoms. Why that shape? Why is the cube the holy grail?
It goes back to that idea of compressing the spring as much as humanly possible. A cube forces those 8 nitrogen atoms into these highly unnatural 90-degree bond angles.
Which nitrogen hates.
It hates it. It wants to be straight, or at 109.5 degrees. Forcing it into that sharp right-angle geometry stores a truly colossal amount of energy. It's the nitrogen version of an already powerful carbon explosive called octanitrocubane.
The geometry itself is the bomb.
Yeah.
So How much more powerful is this theoretical cube compared to the N-chain they actually made?
Well, the predictions are that cube NCU4 would have the highest energy density of all the N-Euro and isomers. The heat of formation is calculated at 16.62 kilojoules per gram. That is a staggering amount of potential energy just waiting to snap back into 4 N-Euro molecules.
Okay, translate that into performance for us. For an explosive, the key metrics are detonation velocity, the speed of the explosion, and the pressure it generates.
Right. And for the N-Euro cube, we're talking about numbers that are superior to anything currently in existence. The predicted detonation velocity, D, is 11,620 meters per second. The detonation pressure, P, is 61.1 gigapascals.
11,620 meters per second. That's over 11 kilometers a second. The speed of sound is what, 343 meters per second? This is over 34 times the speed of sound.
It's incredible. The current top-of-the-line HEDM is a molecule called CL20. Its detonation velocity is around 9,400 meters per second. The N-cube just blows it away in both speed and power.
And for space exploration, the other huge metric is specific impulse. That's basically rocket fuel efficiency.
And that's where N could be a complete game changer. Cube N-4 is predicted to have a specific impulse of 436.2 seconds.
And CL20
It's 272.6 seconds. It's not even close. This kind of improvement means that with the same weight of fuel, you get vastly more thrust.
If these numbers are even close to reality, this is the kind of leap forward that lets you genuinely rethink deep space missions. It's the difference between a propeller plane and a jet engine.
It's a huge leap. And all of it, whether it's the polymeric solid, the linear Nia, or this theoretical N-Euro cube, it all comes back to the same fundamental chemistry, overcoming that one stubborn triple bond.
So let's try to wrap this all up. What are the key takeaways from this deep dive into the world of polynitrogens?
Okay, first I'd say is that the stability of the N-Euro molecule is everything. By forcing nitrogen into these heavier allotropes, these N-Euro molecules, you're basically creating compressed chemical springs with massive amounts of stored energy.
Right. And second, the synthesis of hexanitrogen, NO, in 2025 is a massive, tangible breakthrough. It's proof that you can actually isolate these things. They're incredibly energetic, 2.2 times TNT, even if you do have to keep them on ice.
And third, the computational frontier shows what's possible. These highly strained structures like the N-Euro promise performance that just dwarfs our current best technology, all while being completely non-polluting.
So if chemists can figure out how to make these N-Euro molecules affordably and, stabilize them just enough to be practical, to be shipped and stored, this is a complete paradigm shift. It's unlocking one of the most powerful chemical energy sources we know of with the ultimate green byproduct, just air.
It's the ultimate clean energy release, provided we can solve the problem of, keeping a bomb in the freezer forever.
Which leaves us with a final provocative thought for you to chew on. If scientists do master the incredibly difficult task of making and controlling these unstable nitrogen chains, what's going to be the bigger challenge? Controlling the material's instant, powerful energy release, or just making enough of it to power the next generation of deep space missions?
Something to think about the next time you take a deep, very stable breath of air.
Thanks for joining us for this deep dive. If you enjoyed hearing about the explosive power hidden in plain sight, be sure to subscribe and share the show. We'll see you next time.